In this video, let's talk about metastability in flip-flops. So let's recall what a edge-triggered flip-flop was. So edge-triggered flip-flop is a simple circuit that has one input, a D, and the clock as its input, and has an output Q bar. The output, which is Q, is transparent only during the rising transition of the clock. So if you look at the timing diagram of this circuit, the clock is a periodic signal that comes into the circuit. This is a element that works at the positive edge of the clock. So if there is an input D which is varying over time, then for Q to follow D, what we want is that D should not change sometime before the rising edge of the clock, which is known as the setup time, and D should remain at where it is for a whole time after the edges come. And if that condition holds, then you see that the output Q follows D, and we define two times, a CCQ time and a PCQ time. So these two times bound the time at which Q will actually respond to the input signal. So this is what we've seen already in a flip-flop. Now what we're trying to look at here is this setup plus hold kind of define what is known as an aperture for the circuit. That is, we're saying that during this bounded time around the clock edge, the output has to be stable. So now it obviously asks the question or begs the question as to what happens at the output of the flip-flop if D changes in this time, right? How do you think about what happens to the output of the flip-flop? So as we looked at in our previous videos, we know that when such a transition happens, that is when D transits during which violates either the setup or hold, what happens is that the output will have a valid logic value eventually, but it turns out that the actual value of the output is indeterminate. Therefore, we don't allow it because we can't predict whether Q is going to hit a logic value or a logic value of 0 or a 1 when it talk about a single bit flip-flop, right? So what we can say is that the output of the flip-flop, remember they're all made up of transistors and capacitors, so the output can momentarily reach a 0 or VDD, but eventually the output will settle to some digital value. And when I say digital value, it's going to either settle down to a, since this is, we're talking about CMOS technology, this is going to settle down to either a 0 or a VDD or a 1, right? Now, this time that it takes to settle is something that we need to be cognizant about, right? Because remember, when you design this in a actual product, you will take precautions to ensure that D does not change during the clock, right? But by chance there is some freak incident and it does happen, we want the flip-flop to quickly settle down, right? So we want this resolution time, right, to be as small as possible. I know it's going to be indeterminate, but then we can follow it up with an initialization step or something to get the flip-flop back to its ground condition, right? So this T resolution or T res is an unbounded period at this time. Now, if you think about a flip-flop is essentially, we've looked at in our previous videos, is a bistable system, right? And any bistable system, what I mean by bistable system is that the flip-flop generally tends to reside in one or two stable states of the system. Now, between the two stable states of the system, there's usually what is known as a metastable state. So if you think about a very simple bistable system, you can think about a bump on the road and a ball that is rolling on the road, right? Now, right at the top, at the pinpoint of that bump, there is a point at which the ball can remain momentarily stable at this point, right? But what happens is if there is a slight fluctuation in the displacement of the ball, then the ball will either slide into state 1 or it will slide into state 2. So what we normally say is that the probability of finding a system in this metastable state is infinitesimal, and basically when you deal with real systems, any noise when coupled into the system is going to push the system either into stable states 1 or 2, right? Now in the case of a flip-flop, what is that going to be? Now let's assume that the input of the flip-flop changes at some random time during the clock cycle. So if it changes at some random time during the clock cycle, in all fairness, we should treat this resolution time to also be a random variable, right? Depending on when the input changes in the clock cycle. But we do know something about this resolution time, is that when the input changes outside the aperture, that is when the input changes prior to the setup time or after the hold time, then the resolution time is given by PCQ, right? So as long as we satisfy the aperture, the resolution is accomplished, and it is accomplished within a PCQ time period. So the output of the flip-flop will be metastable if you think at time t, sometime t in the clock period, if one, the flip-flop changes or samples a changing input in the aperture, right? We know that that causes metastability. And then the flip-flop is not able to send it to a valid digital value 0 or 1 within that time t, right? So if I think about how to measure this time, the probability that the flip-flop will be unstable at time t, right? For that to happen, one is that the input of the flip-flop should have changed during the aperture, and two, the flip-flop hasn't been given enough time to resolve this fluctuation into a valid logic level of 0 or 1. So let's think about what we're talking here. So this is my clock signal. I have a setup time and a hold time which is defined at the rising edge of the clock, if you will. I have a clock period. And let's assume that I have a D which is switching with some delay of say T switch, right? And so what we want to do is we want to see what happens when D switches within the aperture, right? That's going to cause metastability. So if I think about the probability that the resolution time is greater than some time period t is given by the probability that my d changes within this aperture, right? Because if d changes prior to this aperture, I know it's going to be PCQ. So for it to not resolve up till time t, I need to make sure that this d has changed only in this period, that is within the aperture. And secondly, that once that change has happened, we have not given the flip-flop sufficient time for it to resolve the output to either a valid 0 or a valid 1. Now, the simple thing is the first part. The probability that D changes within the aperture, remember the aperture is part of the total clock period, and since I've assigned a specific time for this D rise, I can talk about the probability that the change occurs during that aperture as switch plus hold plus setup by TC. Now if switch is 0, this would have just been the width of the aperture by the total time period of the clock. Remember, this is a flip-flop, so it's going to happen only around one of the rising edges of the clock. So be it the rising or the falling edge, right? So this is the probability that the input changes in such a way that it causes metastability at the output. So once we've ascertained this probability, our next step is to figure out how long does it take for the flip-flop to come to one of its stable states, right? So now let's think about that a bit. Like how do we identify this unresolved probability, if you will? Now let's think about the flip-flop. Now if we have looked at latches, we've seen that we can model the flip-flop basically as two back-to-back connected inverters, right? So the flip-flop can be thought of as two back-to-back connected inverters, and this system is essentially bistable because if a 0 is stored here, then a 1 is stored at this node and a 0 is stored back at this node, and the system remains stable as long as the logical value of the 0 remains 0. Remember in the SRAM, for example, when you want to measure the noise margins, right? We want to see how much noise can it be tolerated here before this 0 becomes an undefined parameter such that this output becomes undefined. So now this is the model of the flip-flop. So if I think about the DC characteristics of the flip-flop, right, I can talk about an output voltage and an input voltage. And I can model the output and input voltages. That is, if I talk about these two voltages, right? I can model them as an very steep transition curve between the input and output. Now, ideally, we want this to be as straight as possible, but in reality, we know that all inverters are not perfect. So we can talk about a small signal gain around the VDD by 2 point, and that small signal gain, let's call it some G, right? So in an ideal case, I want this G to be as high as possible, infinite, right? Now remember that this is an inverter. It has a certain drive strength. It has capacitances associated with its source drains, with its interconnects. You may have it, whatever you have it. So if I want to think about this flip-flop in its transitory state, I can model it as an amplifier with some gain G. Now this is what the flip-flop looks like around the metastable point. So it has an amplification gain of G, right? It has a driver resistance and it has a capacitance C. Now this R and C are going to be determined by the design of the flip-flop, by the size of the transistors, by the topography that you've used to design the flip-flop. And so if you think about the metastable point of the circuit is exactly at this point when, again, remember V in and V out are digital signals, so they swing between 0 and VDD. So the metastable point is going to be when V in is equal to V out is equal to VDD by 2. Now, near this metastable point, we spoke about the small signal gain. So what do I mean by that is, if the V out has been disturbed by some delta V, that means the V in has to be disturbed by some much smaller amount, which can be thought of as delta V by G, right? So ideally, because this G is going to be very large, a small disturbance in the output can cause a very large disturbance at the output, right? So delta V by G is the disturbance at the input, delta V is going to be disturbance at the output. So now if you think about the current in this resistor, the current in this resistor is nothing but V out minus V in by R. And this current is what is going to be charging up this capacitor during the small signal analysis, right? So during that, near the metastable point, if you will, when this V in changes slightly, V out changes more, and the net current that is flowing into the output capacitance can be thought of as flowing from driver resistance R into some output capacitance C. And this current is what is charging up this capacitor, which is ultimately determining the final value that you're going to get at Vn of t, right? So if you think about IR of t is given by V out of t minus Vn of t by R, and that charges up the capacitor. So the characteristic equation of the circuit is C dVn by dt is IR of t. So this current that is flowing through the amplifier is what is going to be charging up the output capacitance. And so if you solve this equation, right, what you get is dV out by dt. So if I express the equation in terms of dV out, I get dV out by dt is G minus 1 by RC into V out minus VDD by 2. And what is the initial condition? The initial condition is given by V out is disturbed by some delta V value. Right? So, because what I'm trying to see is when I disturb the output, right, the input is, there's going to be a feed forward loop setup, right? This is a metastable state. So there's going to be a positive feedback that's going to be set up in such a way that it's going to push it to either one of the logic 0 or logic 1 states at the output. So if I solve that differential equation, it's a first order differential equation, so I get an exponential, and the V out of t can be thought of as VDD by 2 plus delta V exponent of G minus 1 t by RC. Again, this, remember we modeled this as an RC network, right? So if you look at it, depending on the magnitude of delta V, right, or the sign of delta V. If delta V is positive, then V out is going to be pushed towards VDD by 2 plus VDD by 2, so it's going to go to VDD. Else it's going to go down to 0 if this is negative. And it's going to go with the speed of RC. So RC is the time constant, right? So if you want this V out to rise quickly, you want to keep this RC as small as possible. What does that mean? That means you want your driver resistance to be as small as possible. You want your output capacitance to be as small as possible. What does the driver resistance small mean? Driver resistance small means that you want your drive strength to be very high. Also, it is determined by this G, right? And so again, you see that the G determines whether the higher the gain, the faster the output is going to settle, right? And so if I want to find the resolution time, right, that it's required to reach VDD or 0, I can write mod delta V exponent of G minus 1 T res by RC is equal to VDD by 2. Why do I use delta V mod? Because this V out, depending on what is the sign of that disturbance, can either move to VDD or can move to 0. Right? And so that gives you that T res, or the resolution time, is proportional to RC, it's inversely proportional to G, and it's related to this delta V, right? So depending on the initial disturbance, the resolution time is also going to change. And so what you see is the key parameters, right? You want your resolution time. If you want it to be so small, it means that your RC constant has to be small. The larger the inverter, the better the resolution time. You see that the small signal gain also reduces the resolution time. Hence, we want to push for digital circuits which have very high small signal gain. So as long as it gets near to identical, then this T resolution is again going to be a small quantity. And the third thing you see is that resolution time decreases with increased perturbation. So if I'm going to perturb the system farther from the metastable point, then it's going to reach a stable point easier and quicker, right? For example, if I push the ball very fast from the metastable point, it's going to reach the stable points much earlier than if I were to give it a small momentum on either side. So if I define this RC by G minus 1 as some time constant tau, then suppose I want to get a resolution time of T res, that means that my initial disturbance on the output should be delta V res, which is given by VD by 2 into exponent of minus T res by tau. Right, so an initial disturbance of delta V res on the output is going to ensure that the resolution time is at T res. Now remember, we're still doing this to figure out what is the probability that the output of the flip-flop is still unresolved after a time t, right? So let's assume that this bistable device is sampling the input when it's changing, right? And let's assume that this input, without a loss of generality, we can say that this input is uniformly distributed between 0 and VDD, right? Again, this is primarily because we don't know anything. We are treating the input as a purely random variable, and we're treating it as a uniformly distributed random variable between 0 and VDD. In that case, the probability that the output hasn't resolved after T-res depends on the fact that the initial output is sufficiently small, or in other words, as long as the output hasn't changed by delta V-res, there's no way that my resolution time is going to be T-res. So if my output hasn't settled after T-res, it means that my initial disturbance was less than delta V-res, right? Or in other words, if I look at the input should have been less than delta V-res by G, where G is the small signal gain of the bistable element. And so therefore, the probability of the unresolved output comes down to essentially probability that Vin of 0 minus Vd by 2 is less than Vres by G. Now remember this Vin of 0, that the disturbance can either be positive or negative, right? If the disturbance is positive, my output is going to swing to Vd. If my disturbance is negative, then my output is going to swing to 0. So I see it on both sides of this Vdd by 2. So in other words, therefore, if I treat it as a uniformly distributed variable, this probability is going to be given by 2 times delta Vres by G times Vdd. Or in other words, it's 1 by G exponent of minus T by Tres. Right? So that's the probability. So again, see, this probability that is going to be unresolved is inversely proportional to the small signal gain. So the higher the small signal gain, the quickly the flip-flop responds, right? And secondly, you see that it's inversely proportional to the time t, or sorry, it's exponentially dropping with time t, which means that as t goes very long, this probability falls to 0. And so if I put this all together, I see that the probability that the flip-flop hasn't resolved the output for some time greater than t res is essentially given by this: some prime pre-constant or pre-multiplier times exponent of minus t by t res, right? So this t is going to determine, the longer this time t is, the lower the probability is, which means that as this t goes very high, this probability drops to 0. So in other words, what we are trying to tell you, or what we are trying to understand from this, is that for a good digital system, as long as your flip-flop is able to respond quickly and with a large gain to disturbances, you're making the flip-flop more and more ideal, which means that you're giving it more power to push to a valid digital value earlier. And so, in most cases, what this means is that if you wait long enough, right, like if you wait a few multiples of PCQ, then with high confidence you can say that the flip flop would have reached a valid output level, right? So, this is something that you need to factor in case you want to worry about freak failures. In that case, once in a while you want to check that as long as you wait, if there is a freak incident and the flip flop goes out of whack, as long as you wait for some time, which is a few multiples of PCQ, you're going to ensure that the flip flop has resolved to a valid output level. And once that happens, basically you're not losing a lot of power. Once you have a valid output level, you know that then the leakage has come down. There is no static power, there's no dynamic power dissipation. The flip flop is back to a digital value, and then you can reset it and continue with processing.